Welcome back, everybody. Welcome to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from the Electrical Engineering Department at IIT Hyderabad. So, in the previous class, we finished with our fifth module, which was understanding the NAND flash, both the cell and the array. So, as we had discussed the last time around, this is a good time to recap what we have been studying because we have finished the first part of our course. So today we will be doing a recap of modules 1 to 5. So we began the course by understanding there has been a paradigm shift in the way human beings have been doing computing. So remember the examples that I gave you from 1970s to late 2000s, I would say that the paradigm of computing was logic centric. This was given through an example of computer aided design. The nature of computing was such that you give structured data to the system, you expect some deterministic solution, and therefore it was called logic driven computing. So you had to do just a lot of number crunching. However, if you notice how the 21st century workload has changed, it has become more data-centric computing. The inputs to the system is generally unstructured data. I'm talking about AI/ML algorithms. And the job of these AI/ML algorithms is to do heuristic pattern recognition and classification. Okay, so what enabled this huge dramatic shift in compute paradigms? We looked at that also. The reason is these incredible advances in memory and storage technology. And that was the primary motivation of running our course. Okay. But however, we also noticed that although the compute paradigm has changed drastically, the fundamental architecture or the hardware architecture on which these algorithms run have not changed quite drastically. And that gave us the opportunity to look at the von Neumann architecture. So I have presented in front of you the von Neumann architecture with its unique, both spatially and functionally separate logic and memory units, which are connected by the data bus. This kind of von Neumann system is deterministic in nature. Basically, it is programmed and also it is sequential, it is clocked. And therefore, because of its sequential nature, there is very limited parallelism. Remember, we compared this with the hardware infrastructure of the brain. Why do we care about the brain? Because all your AI/ML algorithms are also inspired from the computational infrastructure of your biological computing. So there we saw a fundamental mismatch between the data-centric paradigm and how the von Neumann architecture is built. And we saw that when there is frequent transactions between the logic and memory in data-centric computing, this data bus will become the primary bottleneck. And that is what we termed as the von Neumann bottleneck. Before we get into all this, we decided that the first part of our course, we will focus on the advances in memory and storage technology. So that has been our primary focus. We saw that actually memory and storage technology is not just like a simple box as indicated in the von Neumann architecture, but it is integrated in modern day computing systems in a very hierarchical manner. And we saw what is the reason for having this kind of hierarchical architecture from an example of personal finance. I hope you remember that example. So here I have presented the so-called memory hierarchy. At the top is your logic or CPU subsystem, followed by your L1, L2, and L3 caches, your main memory, and your primary storage. So you also have your secondary storage in server kind of systems, but your caches, your main memory, and primary storage are your primary elements of memory and storage in modern day computing systems. So they are arranged in a pyramidal fashion to indicate that as you move away from the logic CPU, what you are essentially doing is you are compromising on the speed to gain on capacity or bit density, right? And this is why we kind of had to decouple the memory from storage in our definitions. Why? Because memory is intrinsically tied to operations of your logic CPU. So it is very tightly coupled to CPU, and the idea is to store only relevant data which is immediately needed by the CPU, whereas storage is more from the perspective of data preservation. Finally, we also discussed that there is something called storage class memories, which there is a lot of development happening for storage class memories, which will bridge the gap between memory and storage devices. Basically, you will have very high bit density along with high speed. So but that is still under works, and that is what we will be discussing in the next part of our course. Okay. Also, we saw that by definition your memory is generally volatile in nature, whereas your storage is non-volatile in nature. So what is the meaning of volatile, non-volatile? Please try to recall. Volatile is if you switch off the power supply, does your data stay or not? In volatile, it does not. In non-volatile, it does preserve the data even after the power supply is switched off. Also, we looked very carefully at the memory hierarchy from the perspective of memory technology. And this makes a lot of sense is because of the trade-offs that we spoke about, that is inherently embedded in your memory hierarchy. As you can see, the composition of L1, L2 and L3 caches is this so-called 60 SRAM cells. SRAM cells made out of 6 transistors. So quite bulky cells. And the idea is that you would want very low latency or very high performance, but you have to compromise on the area or the bit density. Next, coming to 1T, 1C DRAM cells. In 1T, 1C DRAM cells, you significantly reduce the cell area from roughly 150 to 300 F squared to just 6 F squared in DRAM cells. So basically the focus is now more on bit density also, but you cannot just compromise even in latency when you come to the main memory or the DRAM cell. Next, we looked at even the NAND flash cell. The NAND flash is primary storage nowadays, the heart of solid state drives, and this is composed just of one transistor. Okay, so basically the idea is you make the storage element or memory element smaller and smaller, but you compromise on latency. So I will not discuss right now on eNVMs because we are yet to cover that in detail. Following this, we saw some very practical examples of memory hierarchy. In the practical examples of memory hierarchy, we looked at your tear down of two pieces of computing devices some of you might be using in your daily lives. So one is your Samsung Galaxy S20 and the other was your MacBook Pro. I myself use a MacBook, not a Pro, but Air. And what we saw is, yes, the strict definitions are very important, but actually in implementation, memory hierarchy is very, very fluid. How did we see that? We saw that generally what we saw is DRAM is out of chip memory. Why is it out of chip? Because the 1T, 1C, especially the capacitor fabrication is not compatible with the fabrication of advanced transistor technology nodes. They are made in completely different fabs. However, in Galaxy S20, we saw that the DRAM was co-packaged along with processor. And later on in our studies, we saw that was possible through heterogeneous integration. In MacBook Pro, we also saw the big differences in footprint versus capacity between the DRAM versus the NAND flash. So you see, this is the DRAM, whereas this is the NAND flash. They look similar in memory, but the DRAM is just 4 GB, but the NAND flash is 256 GB. Now that I have taught you both DRAM and NAND flash, you have a clearer idea that despite the chips looking the similar size, why is the capacity of NAND flash much more? Also, we looked at what is NOR flash versus NAND flash, which is random versus sequential storage. The differences between NOR flash and NAND flash we had discussed much more in detail when we saw our flash section. Okay. After this, post this, we started looking at global memory market trends. So we saw that the entire memory and storage market can be roughly subdivided into two main components. The first is your standalone or your off-chip memory market that consists of your DRAM, your NAND flash, your NOR, and your new eNVM memories. And this is roughly worth 140 to now almost $180 billion. And the main companies that captured this space is Samsung, SK Hynix, Micron, and WD, who are manufacturing the latest DRAM and NAND flash technology. However, we have to recognize that there is an on-chip memory component also. Remember, your SRAMs is essentially part of L1, L2, and L3 cache. So their primary manufacturers are your manufacturers of advanced technology nodes such as Intel, TSMC, Samsung, etc. And we were very surprised to know that the size of the on-chip embedded memory and that of your standalone memory, the size is roughly the same. This is because on-chip memories in your latest transistor technology node is very, very expensive. Okay, so we discussed earlier that SRAM, you don't really care about cost, but you want to optimize on performance. There are two other important factors that we saw when we were looking at global memory market trends. The first was recognizing the fact that the global memory market is very, very competitive. It's a very fast moving business and it is driven by technological breakthroughs and technological innovation. And within a very short period of time, technology changes very rapidly. And as a result, if you want to stay competitive in this market, you better innovate very quickly. Okay, so this is a business where if you snooze, you lose. Okay, the second thing that I wanted to highlight is there is a rapid increase in terms of CAGR percentage, cumulative annual growth rate percentage, in the eNVM market because a lot of innovation is happening there and still a clear candidate what will capture the eNVM space not yet figured out. Okay, so moving on, before going to looking at individually SRAM, DRAM and NAND flash, we thought it will be valuable to look at a generic memory array architecture because this gives you the importance of how memory peripherals are organized for effective read and write into the actual memory arrays. And we saw that a generic memory array is organized in pages. Now, what is the definition of a page? A page is the same as the number of word length. Remember, word length is the addressable data size of your CPU data bus. And these K, which is the word length pages, each have 2M columns. So therefore, the number of vertical bit lines from where you will finally extract one bit of data is K into 2 to the power of M. Also, we saw that the number of word lines, which is the select or enable signal to an individual memory cell, is 2 to the power of N. For a constraint of square matrix array, we studied why square matrix is very valuable. It is to improve on latency and reduce on RC delays. The number of word lines is assumed the same to be the number of bit lines, and that puts a constraint on the values of M and N. Also, since each cross point between a word line and bit line is one memory cell, The size of the memory array is nothing but the number of word lines multiplied by the number of bit lines. Next, we looked at two important components of the memory peripheral, which helps us, as I said, in reading and writing data into this memory array very effectively. It consisted of your column mux. So the job of the column mux was to receive all these bit lines, k into 2 to the power of m bit lines, and convert them in just 2k bits. So there was a column mux which took k into 2 to the power of m digital bits, and depending on the address that was asserted, you either are able to read or write into just k bits. Okay. Next is your row decoder. The row decoder, job of your row decoder was to select which one of the word lines is to be enabled or selected for the readout or write into. Also, we saw that there are some other important analog peripherals such as sense amplifiers, which detects differences in voltages, the pre-charge circuit, which pre-charges the bit lines to whatever voltage is necessary, and write drivers. Finally, we also saw the concept of memory array efficiency. We saw that memory array efficiency is a very important concept because it tells you what is the percentage between consumed by the array versus the total memory area. And we saw that in NAND flash this was maximum, simply because the memory array is really high density, followed by DRAM, followed by SRAM. So for NAND flash, the percentage of memory array efficiency is roughly 80%. For SRAM, it is 60%, 60 to 70%, and for SRAM, it can be as low as 40 to 50%. Okay, next we moved on to looking at your SRAM. So remember, your SRAM was right at the top of your hierarchy. It formed the cache memory, and therefore always the focus was on performance. So you could compromise a little bit on the bit density, reflected when we saw the 60 SRAM cell. So your 60 SRAM cell stores just one bit of information. How does that happen? The 6 transistors, out of the 6 transistors, the 4 transistors which I have marked out, 2 pull up transistors and 2 pull down transistors, form a latch design or a cross coupled inverter design. And you have these 2 access transistors, which are NMOSs, which give access to the bit lines or to the outside world to the information in the internal storage nodes N1 and N2. Also, it was interesting to note, why is your cross-coupled inverter behaving like a memory element? And we saw that that is only possible because of these so-called butterfly hysteresis loops. These butterfly hysteresis loops, through the concept of positive regenerative feedback, was able to negate any noise that comes into stable storage node. So if a small bit of noise comes into the internal storage node N1, we saw that while bouncing off the memory hysteresis loops, it again comes back to its original position. So this positive regenerative feedback was responsible for making sure that this system has a reasonable noise margin. Next, we looked at the read operation. The read operation started by pre-charging the bit line and bit line bar to the value of VDD and then asserting the word line. Please try to recall that the read cycle was initiated by the node N1 where the value stored was 0. Okay, and the moment you turn on the word line, this particular path from PG1 to PD1, you could have a read current. But this read current does not flip the storage node N1. So essentially we have non-destructive read only by the virtue that you have maintained a cell ratio in the design of the SRAM cell. What was the cell ratio? You ensured that the strength of the pull down transistor was much more than the strength of the pass gate transistor. Since both are NMOS, you ensured that the width of the pull down transistor was much greater than that of the pass gate transistor. Next, moving to the write operation. In the write operation, the principle that we used was you just try to overpower the internal node and try to flip the bit in N1 from 0 to 1 and from N2 from 1 to 0. Opposite to what happened in the read phase, the write phase was initiated from the branch which contained the value 1. So 1 to 0 transition happens first, and then 0 to 1 transition happens next. And all of this was facilitated by pull ratio. Remember what was pull ratio? Pull ratio was ensuring that the strength of the pass gate NMOS transistor was much greater than that of the pull-up transistor. And as we saw, since pass gate transistor is NMOS in silicon has more strength even for equally sized PMOS. This is because the electron mobility in silicon is higher than that of holes. You don't really have to worry so much about the pull ratio. The next thing that we studied in SRAMs is looking at the static noise margins. So we saw that static noise margin was defined as the smaller of the two squares that you can fit into the butterfly loop. We also saw because there is a disturbance, small disturbance in the internal nodes during read operation, the read static noise margins are less than the hold static noise margins, because as you can see, I have presented in this graph the read butterfly loops, and that has shrunk. That has shrunk because your voltage of internal nodes do not read exactly 0. Okay. Also, we saw that this read static noise margin is what limits the scaling of the supply voltage. As you can understand, when you start reducing the supply voltage, the size of the hysteresis loops will also shrink. So will the read static noise margin, and that will create a lot of reliability issues. Another thing that we saw is that there are these very distinct read-write conflicts when you compare with even noise margin. As we saw in the previous slide, the cell ratio ensures that PD-NMOS should be stronger than PG-NMOS, and the pull ratio ensures that PG-NMOS should be stronger than PU-PMOS. And as a result, we will have that PD-NMOS should be much stronger than PU-PMOS. But this gives you a very unbalanced inverter design, and this will compromise on your noise margin, because remember, noise margin was the smaller of the square that can be fit into the butterfly loop. So having any kind of unbalanced inverter designs is not good for noise margins. So what was the solution? The solution was to first look at read and write assist biasing schemes, but more interestingly, look at completely decoupling the read and write operations through your AT-SRAM cell. So remember, in AT-SRAM cell, the write was happening in your conventional manner, but your read was happening through these two extra transistors M7 and M8. And as we know, the latest generation of SRAM is actually built on AT cells because they give you much better stability in terms of read and hold noise margins. This is because the read and write are decoupled. Finally, we looked at some of the technological considerations in SRAM scaling, which is similar to transistor scaling or logic transistor scaling. And also we looked at some technology qualifiers through the Shmoo plots. Next, we moved on to the DRAM main memory. Remember the example I gave you for designing DRAM main memory, the DRAM main memory is more like the all-rounder in a cricket team. So here in DRAMs or in the main memory, you would want very high density, and also you cannot compromise on performance. So this is a very unique combination. However, we saw that intrinsically the DRAM cell and the DRAM subsystem has a performance limitation, and this limitation is growing when you compare it with the advances in CPU transistor technology. And this large mismatch between the bandwidths is something called the memory wall, and the memory wall has been specifically detrimental when we started moving from logic-centric computing to data-centric computing. So the first solution we looked at is making sure that your DRAM subsystem architecture is very robust, and that was critical in somewhat elevating the memory wall. So you try to make sure that you have as much parallelism as possible, and that was possible through this inverted pyramidal architecture of your DRAM subsystem. So right at the bottom, you had your 1T1C cell, which got integrated in forms of row and columns. As you can see, these 1T1C cells had integrated in form of row and columns. These row and columns were then integrated in form of banks. As you remember, generally a bank has 8 such arrays of rows and columns, which then gets integrated into a single chip. So here you see generally 8 banks go inside a chip, and 8 such chips forms one rank of a dual inline memory module. Okay, and processor through single or multiple channels actually interacts at a time with one rank in a dual inline memory module. These dual inline memory modules is something you might have seen or even bought yourself. You might have taken them from Amazon and you might have fit it into your CPU motherboard slot. Okay, next we started looking at the DRAM cell architecture. The DRAM cell architecture is very simple. It consists of one transistor, which is your access transistor, and one capacitor. And the storage node is the most important functional element here, which either stores bit 1 by storing VDD, or it stores bit 0 by storing 0 voltage. Also, we saw what is the mechanism of read in the DRAM cell. What you effectively do is you pre-charge your bit line to VDD by 2. What was the reason for pre-charging it to VDD by 2? It is very simple. If the stored value was VDD or bit 1, there will be a discharge because of positive gradient from the storage node to the bit line. Whereas if the value was 0, then there will be a negative gradient. So current or read current will flow into the storage node, and any such positive or negative read current will charge or discharge the bit line, and therefore that can be detected from your sense amplifier. Also, through our charge transfer analysis, we came to the conclusion that the charge transfer ratio, which is the ratio between CSN divided by total capacitance, which is CSN, the storage node capacitance, and the bit line capacitance, is a very, very important parameter, because the change that you see in your sense amplifier is directly proportional to this ratio. Therefore, you have to maintain some reasonable value of storage node capacitance as you keep reducing the dimensions of your DRAM cell, and this becomes the key scaling challenge. Also, we saw that in addition to this destructive read, and even during hold, the several leakage mechanisms from the storage node, there is a need for continuously refreshing the data. How do you figure out what should be the refresh rate? it is determined by looking at the cumulative probability percentage of the retention time distribution inside the DRAM cell, and the JEDEC specification suggests that at least 1e minus 6 percentage of cells should meet the specification of 64 milliseconds of retention time. Also, we saw that the concept of refresh happening every bank along with the concept of interleaving helped in improving the throughput of your DRAM subsystem. Finally, we looked at the scaling challenges and approaches to solve these scaling challenges. First, as I had mentioned, the primary scaling challenge in the DRAM cell was trying to scale the storage node capacitor. So, before 70 nanometer node, we were using the so-called trench capacitor, which had an area scalability only of 6f squared. Recently, we have moved to the stacked capacitor, which has an area scalability of 4f squared and much larger aspect ratio. So, larger aspect ratios are very important in making sure that the area of the capacitor is increased. Remember, we had all these very strange looking high aspect ratio structures because you wanted to have more surface area in a small footprint. Also, we saw how by having specially designed recess gate transistors and further versions such as saddle FinFETs and buried gates, you can scale the access transistor of your DRAM cell. The philosophy of scaling the access transistor was to reduce your off-state leakage and as far as possible to reduce the leakage mechanisms which will prevent frequent refresh. Finally, we saw that there is a lot of activity happening in improving the integration density of DRAM cells by introducing advances in packaging technology. We saw the example of your embedded DRAM, which was integrated on chip to a logic chip through monolithic integration. Whereas using 2.5D or 3D heterogeneous integration, we were able to have the concept of high bandwidth memory, where logic chips and DRAM chips, which were fabricated using entirely different processes, were integrated through TSVs or through silicon vias. Finally, we come to our latest topic, which is your NAND flash cell. Since the NAND flash cell is your main storage element, remember the focus was more on having very high bit density and non-volatile operation, even if it comes at the cost of larger latencies. To have very high bit density in the flash cell, we decided that we will somehow modify just one transistor to change it from a logic element to a memory or storage element. And this was possible by modifying the gate stack of the transistor. So, gate stack of a logic transistor generally has just an oxide and a metal, but a flash cell has a 4-layered structure of tunneling oxide, charge storage layer, blocking oxide, and control gate. And by introducing and removing charges from the channel into the floating gate, you were able to tune the threshold voltage of the transistor. So, when there were charges trapped inside the charge storage layer, the threshold voltage of the transistor was more than the read reference voltage, and therefore the transistor was off, and therefore program was called state 0. And when you removed the trapped charges from your storage layer, you went to the erase state, which is state 1. This is because the threshold voltage was lesser than the read voltage, and therefore the transistor was in on state. Next, we move to study the differences in the organization of these flash cells. This was the NOR organization versus NAND organization. Remember, NOR was your parallel organization where the source of each cell in the array was connected to the source line and the drain was connected to the bit line. This resulted in a large area per cell of 10F squared for NOR. Whereas the NAND, by the virtue that it had sequential architecture, the cell size was limited only to 4F squared. This was further improved using bit scaling and vertical 3D scaling. So, NAND flash gives you very high bit density, but it comes at the cost of sequential access. Next, we started looking deeply into the array level operation biasing schemes for both program, erase and read. Now, erase was relatively simple. It was done at the block level. The program and read had lot of intricate biasing mechanisms to ensure that only correct page is programmed or read out. In the program cycle, while the word line of the appropriate page was given a very high voltage of 20 volts, the remaining word lines were just given enough voltage to allow the bit line voltages to pass through. Just enough to turn on these transistors. Remember, the GSL during program operation was cut off to ensure that there is no string current during program operation and all of the charge transport is facilitated only in the direction from the control gate to the channel. Also, through a very interesting concept of inhibit voltage on the bit line of the cells you did not want to program or wanted to leave in the erase state, you ensured that you increase the channel potential of these cells, thereby not allowing the dominating Fowler-Nordheim tunneling mechanisms to occur only in these cells. In the read operation, while the page of our interest was biased to the read voltage of 0 volts, all other word lines were again biased such that it, irrespective of the state of the cells, they allow a string current to flow through. Now, since in read operation the flowing of string current is very critical, you ensured both your SSL transistors and GSL transistors were turned on. How was the read finally done? All the bit lines were pre-charged to a small read voltage, and depending on whether the cells of the page where you have applied the appropriate read voltage are in erase state or in program state, either there was a read current if it is in erase state because the transistor is on, in program state the transistor is off, so there was no read current, and as a result there was either a discharge in the bit line or no discharge in bit line. By checking whether the transistor is on or off, you were able to figure out whether it is in erase or program state. The last section that we studied was regarding the scaling in NAND flash cell. Both we looked at bit scaling and 3D scaling. In bit scaling, we saw how by programming intermediate threshold voltages, you can go from SLC, which is 1 bit per cell, to MLC, which is 2 bits per cell, to TLC, which is 3, and then QLC, which is 4 bits per cell. But all this bit scaling doesn't come for free. There is an added component of both complexity and latency. Latency for QLC can be as large as 2 milliseconds per page, where SLC can be programmed at roughly 10 to 100 microseconds per page. We also saw how, using this very nice scheme of incremental step pulse programming, you are able to have a very tight distribution in VTH for both fast and slow cells without compromising on latency. Finally, we looked at the reliability challenges which prevented further scaling of the 2D NAND flash and the introduction of truly 3D data storage through the 3D NAND flash through 3 important modifications. As you can see in the schematic, the first important modification was the organization from lateral string to vertical string, which allowed you to relax some of the design rules. Next, from a 2D cell, we went to a gate all around cell. And finally, to ensure good cost per bit and good scalability in the 3D NAND flash regime, we moved from floating gate transistor to charge trap transistors. With this, we have concluded our part 1, which dealt with understanding advances in memory and storage technology. Next, we move to looking at the very important question: can these memory technology that we have studied now, and also we will look at eNVMs, support more brain-inspired neuromorphic computing? See you in the next class, where we will begin looking at eNVMs, which are storage class memory. Thank you.